Thanks, Mike. What a gentleman. Unlike Hayden, who's been teasing me all week about what we're going to see on the grinder build. Come on, we've got to go and check this place out. So apparently we're going to be seeing something very monumental. I'm hoping it's going to be the grinder, but Hayden just won't tell me. So let's get on over to the R&D facility and see what they've got in store. Sorry, it's got to warm up for about 5 minutes.
5 minutes later.
Here we are. I better not forget my special clearance pass. Come on guys, let's go and say g'day. Gentlemen, how are we? I like the look of what I'm seeing, I guess.
It's just my Harley.
All right, so Hayden promised me that we'd be seeing machine today.
Machine.
Okay, these are machine parts.
Machine.
What's under the wrapper?
Well, yeah, I'm sure you'll know what's under here, but everyone else doesn't. So we've had a part of our R&D team, Frank, that's been around for a long time. I think it's about time you all met Frank. So just let me get in here and you right there, Frank? Yep. All right, good. You ready?
Oh, right. It's Frank.
It's Frank.
I was thinking something a little bit more further down the track than Frank.
Details are important. You said machine. I'm showing you a machine. Frank.
Well, everyone, introducing Frank.
That's right, Frank. Why is Frank here?
Why is Frank here today, Hayden?
Well, not just today. Frank is here for all our prototyping. So in order to get into this project quicker from the beginning, taking an older version chassis and being able to adopt all our parts to it and prove a lot of the concepts that we want to run with, it's much faster to do this and use Frank.
So you don't go and make a prototype of the expected finished version first. You've got to prove it all first.
How do I know where the exhaust headers are going to go? Are they going to hit on the chassis? You don't know these things until you put what's in there that you want. So start off with this, all the bits that you think you want to use, prove them, try them, test them, and then from there you can build your final designs.
So if we're having a bit of a look at Frank, I can see, Frank is short for Frankenstein.
Frankenstein.
Right. It's an old King Concepts machine. I can see Frank's had some bits chopped off, welded on. It's not your standard anymore. And I'm sure, this is like a whole bunch of evolution moving towards the direction that we're going. Test mule, effectively.
Effectively, yeah.
All right, well.
But we're not talking about Frank as a general today.
We're focusing on something specifically, right?
We're looking at the wheel drive systems.
All right, and last week you and Tim were talking about the geometry and the wheels, the size of the wheels, the placement of the wheels, the importance of all of the mechanic side of things to get right. So I think I'm going to step out of the picture, hand over to Tim and you to explain what's happening in here. That all looks massive. I'm not going to get too much into it and give too much away. I'm going to give it to you guys and you can, listen in and have a look at are you going to be showing the new wheel drive system?
Yeah, some bits.
All right, I'm all eyes and ears.
So Hayden, wheel drive systems. I think we talked a little bit about this last week and we said some of the key fundamental elements of a wheel drive system is essentially inserting some kind of drive mechanism to replace what an operator would normally do or historically have done behind a push machine.
Yep.
So that would be controlling the machine speed across the floor. It would be turning it around, rotating, manoeuvring the machine. It would obviously be having to counter the purchase or the grab of the grinding head on the ground as it's grinding, and the abrasives are getting leverage over the floor and creating that torque, and wanting to drag that head from side to side or across the floor. So it has to counter all that. And then of course there's transportation and of the machine, moving from one place to another, getting up and down ramps, all really key things to do with the wheel drive system. Have I forgotten anything?
they're going to have to be a really big unit to keep up with all the operators that were out there doing that in the past. You know, there's no milk crates and run-ups into vans anymore. So, no, look, it's, wheel drives, they're, in an RC, they're critical at the end of the day.
Yep. And we talked about how essentially there's a couple of main components to a wheel drive system. There's obviously the mechanical system.
Yep.
And when we say mechanical, we're talking about the gearboxes and the motors and so forth, the actual components that will carry all the weight, that will drive all the torque and whatnot.
Yep.
Obviously, these machines are getting heavier over time, because we've talked about power weight and why that's really important. So we're making heavier heads with more power. So obviously there's more responsibility or more load on the wheel drive system. So mechanically, we need something that's going to be robust.
Yep.
And then of course, then we need to control that system, and that's a full electronic process as well. So how about we talk a little bit about the mechanical side?
Mechanical, yep.
Again, a lot of what we've mentioned in the past is we've observed a lot of the other alternatives that we've seen in the markets, other solutions.
Yep.
So tell us a bit about some of the things that we've seen in the past, and some of the thinking that's gone into Frank and the systems that we've actually come up with ultimately.
Yeah. So I mean, a prime example of what a lot of contractors out there find is in their PG series machines. Most manufacturers have some sort of issue with their wheel drives, whether it be electrically or mechanically. As we've always discussed in the past, there's trade-offs to everything. There's only so much room you have around your wheel drives. Your electrical cabinets are only so big. So a lot of guys are sacrificing things to meet the need that's required for that machine. Could they do better? Probably, if they had the space, the funds, the availability of parts, things like that. So we have here a wheel drive motor that's out of one of the PG series machines. Now, they've changed them up between their two models, so they have rectified a few of the things that went wrong, but most guys that have got machines would be very familiar with having to replace wheel drive shafts, burnt out pins and things on things like that. That all comes with the bigger and heavier the machines are, the more current they're going to pull coming through all these cables, the bigger the control units need to be, and obviously for mechanical purposes, bigger the wheel drive shaft is, the bigger the gearbox and motor is. So you need room for that, which is always a trade-off of space and again adding weight. So the heavier the machine, the bigger the gearbox, adds more weight to the machine. So it's a bit of a spiral there of what you need to look at. But generally speaking, there's a couple of different types. You've got worm drive gearboxes, helical gearboxes, there's parallel shaft gearboxes. There's a whole range of different things out there that have been tried. Some have passed, some have failed. No one's really sort of hit the nail on the head with a perfect solution out there that we can see in regards to it. So, we've kind of looked at all of these and gone, well, where should we start with trying? We started off and went, let's just go big. Let's go really, really big and work back from there.
Yeah.
So,
look, Hayden, I guess one of the biggest things that I'm thinking about too in the wheel drive system is you basically have a mechanical component where you have to take all the stresses and strains and the force, and then you want to drive that, okay? And we've seen those systems doing the same things where the actual drive elements, whether it be the motors, are carrying or bearing all the load of the machines.
Yep.
Okay, and we've seen systems where they've essentially been separated, okay? Right. So where ideally the motor and the gearbox shouldn't be taking any of the weight of the machine. That should be borne, it should be a master-slave type scenario where they're completely just responsible for motion control. Yep. And of course the rest of the hub or the assembly is there to deal with the drive and the weight. Yep. And to be the beast of burden in the equation, so to say.
Absolutely. And that's why we decided to go really big in the beginning and then maybe scale down if we find we need to. So, as Tim's saying, this is a prime example. This is where we started. We basically took some really big, heavy-duty shafts into some, what we think are, excuse the pun, but unbreakable Toyota hubs. Purely from a strength point of view, just to really be able to gauge with any of our load testing and things like that we wanted. So we didn't have a breaking point within a motor or a gearbox. We knew that they were strong enough, so we had to put something on the other end that was going to be strong enough. One of the trade-offs on all of these things is play in the wheels. So your lock-in mechanism is a really, really critical point of these machines because it's taking all of that shear load of the drive coming through.
Yep.
Now, an example like these, in an automotive sense, they allow a lot of backlash in them for parts to disconnect and reconnect, which in our industry means the head just starts wanting to do this because you've got so much play in your wheel drives. So locking pins, different scenarios like that, they're all designed to move and have play. So that exponential movement is problematic. Plus, you find any of these systems that people are using, they're generally much smaller in size. You're talking M12, M10, M12 size bolts. So you really don't have a lot of strength in those from a shear application. So this is where we started with going. All right, this is what we want to try and do.
So it was. It's fair to say from looking at this that we were a little gun shy when it came to lightweight wheel drive systems. We'd experienced a fair bit of failure in compact lightweight.
That's right.
So this is obviously a reflection of how much we wanted to move away from a lightweight system. Like you've said, great, heavy duty, unbreakable, but it's not really compact enough, is it?
Not compact and doesn't quite fit the application.
Yep.
So from there, we kind of decided, well, it's going to be a custom solution. So we put all our heads together and went away and looked at just some samples of what we've come up with around some of these mechanical solutions. Again, it's not the entire solution of it, but when we look at a small thing like this, you've got little bearings there that are carrying the load of 500 kilo machine.
So 250 kilos per bearing, essentially.
Correct, yep, on there. Same as the shaft size. All of the weight on that axle is pivoting on there. That's not a lot compared to some of the examples over here, Tim, of what we've looked at doing. Just from a bearing perspective, example, that's the size bearing. 2 of these per side is going to be carrying the same weight as that. So just gives you an idea of the robust thinking behind what it is we're trying to achieve here. It's not to say no one can do it. That was a key goal of ours, was wheel drives need to be robust, need to be operating the way we think they should, because the last thing we want is guys having wheels falling off the machine all the time. So,
So I've got this other. I've got a couple more shiny pieces of metal here. Would you care to maybe enlighten us to how they all sort of are part of?
Yep.
When we're looking at this being the existing wheel drive system that many people are, certainly in the Australian marketplace, are very familiar with.
Yep.
And used to. As you've mentioned before, the newer 690 and the 830 machines have a modified system, which has definitely improved on this.
Absolutely.
But of course, a lot of our paradigm and thinking was based on where the market was at the time when we started developing this process.
Correct.
And that was it. So
That's right. So look, our thinking was we wanted the weight of the machine to not be borne by the drive shaft in any way at the end of the day. So we have a boss mount here that mounts up to the chassis and frame of the machine. It then has 2 of these bearings sitting on here with this hub over the top on there, and then our wheels are effectively mounted onto here. So when the wheels are unlocked, everything's spinning on here, and you have 2 great big bearings there taking the load of the machine. So there shouldn't be any issues around how strong those bearings and these parts are going to be. We also moved to a bigger wheel shaft on here, so this would be effectively replacing the output shaft on the gearbox here. So this runs into a gearbox similar to these and runs out, and all of that is covered and borne through here, and our lock-in mechanism, all that has to do is drive in a direction. There's no load on it of any sort. The pins themselves have nothing, giving them angular values of any sort. It's purely straight through, shear load that direction. So we can get a lot more. And again, you look at the size difference on that compared to a 10 or a 12 mil dowel that effectively the others are using.
Those little spring-loaded
correct
release pins, whatever they're called.
Yes. That's right. So once you put a surface area around that, there's a lot more surface area on these from a wear and tear perspective and grab. So
just to clarify, this shaft you're talking about here, that's still not taking any weight of the machine.
Correct.
That is just purely driving
the
power.
That's right.
From the motor and the gearbox combination out to the wheel.
Yep. That's correct.
And of course, probably one other really key piece of information to do with these locking pins is they all need clearance. You need to be able to get them in and out, whether it's the little spring-loaded
that's right.
Dowel pin, whether it's the system that we've come up with in our team here. So they've all got clearance. Now, obviously, the closer this hole is to the middle, okay, the more that clearance or slop will be exaggerated or accentuated out at the perimeter of the wheel. And of course, the bigger the wheels become, a small amount of play in that system becomes more at the wheel. Okay?
That's right.
And that all then gives the machine more freedom on the ground, less accountability.
Yep.
So I guess the point I'm trying to make is we've got our pins located very far out towards the perimeter of the wheel. So to counter the fact that there is a little bit of play, so you can still get those pins in and out, but that play, instead of play being magnified to 5 mil type of slop in the wheel, you're talking about maybe a 0.5 mil clearance.
Correct.
Being retained almost at a 0.5 mil of slop on the actual wheel as well.
That's correct. Yep. Yeah, and that's that we find that is a really important thing for getting a machine just to sit there in a groove and not be bouncing around and trying to take off on you. And we see it so often with guys that their wheel pins are just worn out. They're moving around. They call up saying the machine's just bouncing around everywhere. And 9 times out of 10, it's a problem with that. Or the hub itself is worn, another part is worn, a wheel shaft is worn, anything in there. So, we've really concentrated a lot on trying to make these robust from a wear and tear perspective. So, which is massive.
All right, well, that's a fair bit on the mechanical side of things. There's been a lot of consideration, a lot of iterations and development from that point of view. We mentioned that mechanical is only half the story, half the equation at the beginning of the video.
Correct.
Let's talk a little bit about the electronic part of it, because the experience for the user, obviously, providing these things, their wheel drive system holds together and doesn't break down or get too much slop. The experience to them then comes to how those wheels are controlled. Okay.
Yes.
And that's done through an electronic system.
Electronic
So
wheel controller.
let's have a little bit of discussion about the electronic control for the wheels. Sorts of things that we've seen. Maybe some of the problems that we've actually come across. We see a lot of this stuff in the workshop as we've discussed in the past. Fixed a lot of these things. How have we circumvented some of those things, and how have we rethought the electronic control? And what benefits has that given from a user experience point of view?
Look, probably the big thing to look at here is there's 2 ways that manufacturers can do this. There's off-the-shelf systems, so they're buying a remote control that has a wheel drive controller as a part of it in the receiver, and it that just then basically plugs the wheels in and talks to it. Not a lot of flexibility in what they can do with it. Everything's kind of predetermined for a basic application. Then you go down the route of a bit more customised. So an example of this would be the early HCCs. They had a unit that went basically direct out to the wheel drives, and there wasn't much you could do within them from changing them around a bit. Whereas Husqvarna, they have a circuit board in there that is the PLC, the wheel drive controller, all your charging relays, everything in one big board. Now, on the output of those, a really common problem is burnt out pins on the bottom of that, and that is just that these motors are pulling more current in high load applications than what the board can actually supply to those, or the wiring that's linked in.
So we're talking about a printed circuit board,
correct,
delivering the full motor current to the motors. And what sort of current are we talking about?
Somewhere in the vicinity of about 13 amps.
13 amps DC? Off a printed circuit board.
Printed circuit board.
It's asking a lot from a printed circuit board.
Look, it is, and again, there's different variants within a circuit board. You can design them to handle that, if not more. But that particular one, the connectors they've used aren't quite holding up to that rating. They're probably closer to the 9 amp rating. So I mean, in-house, we've replaced the plugs in the past. For a lot of them, we do upgraded plugs nowadays that are a higher surface area type of pin, soldered straight onto the board. We've seen plenty of customers with them come in where they've just hardwired straight to the board, hoping that would fix it. In some cases it has, but other cases not. So that's a really big one, is from the electronics side, you've got the control side and you've got the delivery side of it, which also falls into the wheel drive motors and how they run, what they're sensing off, if they're Hall sensor, what kind of controls you have. So that is a huge part of wheel drive systems, is what feedback are you getting back from the motors, how are you controlling them. There's details galore in what happens with this. Primarily, I would say, I think out of all the machines I've used, Husqvarna are probably the closest to having a good system from controlling wise. A lot of the others are they have good little functions, but then they have really big drawbacks in other areas as well. So they did pretty well on that remote system. It kind of ticked a lot of the boxes, but it's still very, very jittery. It's not quite as smooth as it could be.
Well, of course, obviously, one complete printed circuit board, which incorporates all those things that you talked about, is nice.
Yep.
It's convenient. It's compact.
Yep.
When it comes to building something into a machine, which we've already talked about, has a lot of space compromises from the beginning. But of course, you burn out plugs and so forth to a point that it's irreparable.
Yep.
You're basically throwing away your PLC and everything else along with it. You're charging relays, etc. Because it's all
one unit.
It's all one unit.
That's
so
right.
I'm getting the feeling that we've skinned this cat slightly differently when it comes to.
Absolutely. We've gone separate modules for each of these. Not necessarily on the basis of easy to replace if one goes, but that's certainly a factor that if something happens to one of them, a machine's not dead in the water because the PLC is a part of it and the whole lot doesn't work.
Yep.
So we've really kept everything modular. Plus, it gives us the freedom of being able to select what components we actually want to use. We're not sort of driven in by, well, because you're using this over here and that doesn't match that circuit board, you have to use this. We've got the freedom to use whatever components we wanted to do the same job.
Yep.
So it's a lot better option, but it's a space requirement is the difference, because everything has its own case built around it. Everything has different terminals coming different places. So yeah, another one of those factors of trade-off of how much electrical space do you have.
So you're essentially talking about components that are fit for purpose, if you want to call it that, or more fit for purpose?
Definitely heavy-duty industrial.
Heavy-duty industrial.
Yeah.
So if we take, say, the wheel controllers for an example, we're talking about, we've got our electric motors that are mounted to the gearboxes, and sitting above them essentially are customised or dedicated wheel controllers.
Yep, one for each wheel.
One for each wheel. Now those wheel controllers are programmable.
Correct.
So there's lots of different features that can be programmed into those things.
Yes. Yep.
But also my understanding is those wheel controllers are there to supply the current, to carry the current load.
That's right.
So any other brains or smarts that are further up in the system, that's all they're doing. It's just brains and smarts.
Right.
It's not carrying any load. It's just making the decisions essentially, or relaying the decision.
Correct.
So, the wheel controllers, just for example, what sort of current can they actually supply?
About 150 amps.
About 150 amps on their own merits to the wheels.
Yep.
Not that we use that much.
Nope.
But we've got the capacity.
Correct.
Okay, and we're not relying on a printed circuit board.
That's right.
To carry that kind of current.
Yeah, and just in general, everything's just heavier duty. All the wiring coming off the motors themselves are heavier duty. Once you get into these next level, not so compact units, everything kind of, the freedom becomes a bit bigger for more industrial settings. So,
and of course, we're always trying to push the element, which we're trying to maximise performance. And when we start talking about maximising performance, we're always talking about pushing the upper limits of components. So 150 amps in a wheel controller sounds like we've got a lot of top end to play with. Okay,
we do.
We're not hitting that. It's not like we're running at 135, 140 amps.
No.
What sort of amps are we typically running in our wheel motors?
20, 25?
20 to 25. So when you take into service life or duty life of components, it's really down the bottom.
It is.
Quarter,
Yeah.
fifth of its capacity. So this means it's going to last longer. It means it's going to perform better in hot environments, particularly when things start to get more stressed out.
Exactly right.
So lots and lots of benefits to up-speccing, so long as you can fit it in the machine.
That's right.
Obviously, there's a cost element that comes with this. These things cost more to have as individual parts as opposed to a fully integrated solution.
Yep.
But I would think that for our user base, where they're all about reliability and performance, those kinds of things pay for themselves pretty quickly.
Very quickly.
I've seen some of the bills that come out of the out of the workshop for replacement parts. I'm sure there are a lot of customers out there that would prefer not to be paying for those things down the track. They'd rather pay it up front, less up front, and then get all the productivity benefits and reliability benefits that come with it.
Just on the reliability, as soon as your downtime on site, that's a big killer. All this is about trying to prevent that. So,
anything else from electronics point of view that we should be talking about that you want to bring up for this conversation?
There's a lot in there. I mean, look, PLC, having a dedicated PLC, completely programmable, just gives so much flexibility for control over the wheel drives. Still example, HTC, Husky, everyone, Wheel speeds are like 1 to 10.
Yep.
Yeah, you kind of just get get a couple of increments in between, but that's about it.
Yep.
We've got unlimited. We can give you 200 different options of wheel speeds if that's what you want.
Yep.
Out of this. So the freedom of being able to make it a finer adjustment in the areas you need it,
Yep.
and a bigger adjustment in the areas you don't need it, is really good. Things like transport speed. Being able to go, okay, well, we don't need to worry that someone's accidentally going to try and polish it, 30 kilometres an hour on a floor.
30 kilometres an hour?
Well, I think the specs were 0 to 100 or something. I'm not sure.
In how many seconds?
2.5. I can't remember. It's something astronomical. But yeah, being able to give people the fine tuning they need in the areas they need. So, in your low down slow cuts, you really want to be able to slow that machine down and get a really nice, set speed that you want. You want to have a range. You want to have, 1 to 20 to be able to select that down there. But then there's a midpoint you don't really use or need, and you get up to polishing, you want to be able to push it a lot faster. So it just gives you the flexibility having all these individual components to be able to do that.
And then you want to go across an undercover car park, and you want to go even faster again, right?
That's right. Yeah, one side of the job to the other. Driving up the road to the next job, maybe.
Yeah.
I don't know.
You don't want to be going at first cut speed.
No, absolutely not.
To go from one end of a shopping mall to the next,
Yes,
right?
That's right.
Yep.
The flexibility is really there in having all these components to make it a lot easier for a customer to use a machine.
Yep. Well, I got the feeling when we come round to talking about the radio control side of things, we'll probably get into that a little bit more deeply because they're very closely linked, connected to each other. So without letting too much of the cat out of the bag today, we'll just park the PLC and the radio control for another conversation for another day. But I think what we've covered here regarding the mechanical component and the electronic, hopefully, we've given people a lot of food for thought and things to think about. So thanks for sharing with that all those different elements with us, Hayden.
You can see the bits I'm excited about.
So that's pretty much
The wheel drives.
the wheel drive system, at least all that we're prepared to reveal today. And or maybe we haven't made the rest yet. Who knows?
That's right.
We'll have to let time tell.
All right, so not really the reveal I was expecting we were going to have today, but clearly all really important things to be covering nonetheless. All I can say for you guys is that lucky these guys are on the task and I'm not. I mean, I probably have something out right now, but can be pretty sure the wheels will be falling off. Speaking of which, I believe you guys have got to get back to making a machine. So next episode, we'll be talking about...
There's still so many things.
You'll be showing us a...
Don't know.
Hey guys, can't blame me for trying. Thanks guys, really appreciate all of the insight that you're giving us into this new machine and hope you guys are enjoying as well. Till next time.